We're going to hear from Efe today. Efe is my from hometown, Denizli, and when he first came to Sabancı years ago, he came to me and found me, and he was interested in doing physics, and we started working immediately. And we had many projects together. Worked in my lab, we worked on detector, background calculations, and then dust scattering halos, and currently we're also working on GRMHD simulations. We did many projects, but it's time for him to go because he already got a PhD position offer from Max Planck Institute, and he has to defend his thesis. I told him pick any of the subjects we've done together and present them should be fine. So he's going to talk about the stuff that we did together. We did most of the stuff on dust scattering halos.
Thank you. Welcome all. My name is Efe Öztaban, and today I'm going to present my master thesis titled Machine Learning-Driven Determination of Three-Dimensional Structures of the Molecular Clouds in High-Resolution Millimeter Images. Before I start my talk, I want to thank my supervisor, Professor Emrah Kalemci, for all your guidance, your trust, and patience throughout the last, 6 years. I also want to thank the thesis committee and also Arkadaş for attending this talk. And also I want to thank to Arkadaş and Ahmet for collaborating with me, and to my family, my parents, and also all the friends coming here and also joining from Zoom, even there in US or South Africa. So this is how I'll structure my talk. First, I'll start with motivations. What are black hole X-ray binaries and how we find their distances? And then how can we use dust scattering halos to find their distances? And then I summarize our test source and the data we use. Then I'll introduce the main challenge with the Apex data to find the 3D structures of the molecular clouds. And because of the existing methods are not working, then I'll introduce the methodology we developed for 3D construction. And then I'll summarize with how we use this 3D structures in dust scattering halo modeling and image fitting to constrain the source distance. And I'll finish with results, conclusions, and feature work. So firstly, what are the black hole X-ray binaries? So they are a stellar mass black hole cooling matter of a companion star. And this matter, as this matter spirals in, it creates an accretion disk and heats up to millions of kelvins and radiates in X-rays. And they are the most extreme laboratories of the nature. They are the systems we test general relativity in strong gravity. There are systems we see relativistic jets, accretion physics, and also there are the systems we learn about the formation of black holes. But in the systems, distance is a master variable, so you need to know distance to infer other parameters. So, for example, the luminosity is 4 pi distance squared times flux. So we have to know the distance to know how bright is the source. And also we need to know the distance to infer the physical size of the disk, jet and wind, also to weight the black hole, and also to know where this black hole located in the galaxy. And there are many standard distance methods to find the distance of the black hole X-ray binaries, but these methods are not working for heavily absorbed binary systems. And actually, they're the ones which are most interesting. So we ask the question, how can we find their distances using a different method? So the solution is dust scattering halos. Dust scattering halos are extended objects when an X-ray photon coming from the source collide with the intervening medium, the cloud and dot structure in the intervening medium. And when they pass through this intervening medium, they scatter. Some of them are scattered in small angles, and that's why they're reaching us. Because they're going a longer path, they're reaching us a bit later and a bit off axis. That's why these perfect circular shapes are forming. But they're not only this perfectly looking shapes, they're also encoding the distance of the source by its geometry. So this, how can we use dust-catching halos as distance probes? So dust-catching halos, their morphology, their intensity, shape, and spectral properties depends on the distance to the source, its intrinsic spectrum, its time history, as well as the distribution of the dust grains and their size and composition. So actually, this simple time delay equation is enough to infer the distance. So for a photon scattered through a dust layer here at a fractional distance of x, and when the source is at a distance of d, these photons scattered through a dust layer with a scattering angle of theta, then we can calculate the time delay of this photon reaching us. And if we know the time history of the source object and also the size and composition of the molecular clouds in the line of sight, we can actually view all these parameters and derive for the d. So we select the test source. It's 4U1647. It's a highly active galactic X-ray transient, one of the most active ones we know. And it's discovered in 1976, and it shows repeated outbursts every few years since. And it's interesting because of its waking behavior, but it has also different interesting features like delayed hard state transitions, very low luminosity soft states, and highly ionized disciplines. But the distance of the source was highly uncertain because it was sitting in a heavily obscured area in the galactic plane. So an earlier study from Emrah Kalemci was trying to use dot-catching halos with a low-resolution CO data to narrow the distance down. But in 2018, the results were narrowed down into two candidates to 4.9 kiloparsec and 11.5 kiloparsec. But after this work, the ambiguity was not resolved because of this low-resolution CO data. So the motivation of my thesis actually overcome this low-resolution issue with using a high-resolution data and with using a pipeline redeveloped. So I'll explain the data we use. So as I said, in the X-ray side, we need the image of the dust scattering halo, and also we need the time history of the source object. So this is the X-ray image we take from Chandra. It's rebuilt, pre-processed to match the apex resolution. So you can see the chip boundaries with green lines in the image, and also you can see the apex field of view with this white box. And on the right side, you can see the time history from an outburst of the source. So you can see the starting of this outburst, a plateau, and then a steep decay. So this decay
is this directly from the black hole? Point source, or
no? This is coming from the point source, but the outburst is happening in the accretion.
Yeah, from the disk.
Yeah, from
the
And this steep decline is actually very important for us to see the dust catching halos, because if we don't have a decline like this, we will be seeing a very bright point source, not these perfectly looking pale shapes. And this also data is created by Swift and M.Sc observations. So we are set with the X-ray side. For the dot side, we use CO tracers for determining the dust in the line of sight. So we use the data from Apex telescope. It's a 12-meter submillimeter telescope located in Atacama Desert in Chile. And we used 12 CO and 13 CO emission lines to detect the cloud structures. And in the data set, there was 500 velocity channels ranging from minus 175 km per second to plus 75 km per second. And each channel is, you can see an example image from a channel velocity. Each channel is 49 by 53 pixels with a pixel scale of 13.6 arcseconds. And from here, you can see the change of the resolution from the previous studies. So Emrah was using these low resolution survey data, but we passed to Apex resolution, so the changes very big. So you can see the Apex data along the line of sight here. So you can see 12 CO and 13 CO data. So we sum up all the channels into integrated brightness temperature and plot it versus velocity. So you can see these peaks, and these peaks are actually candidate molecular clouds. So because the intensity scale was much higher in 12 CO, it makes it easier to detect these molecular clouds. Although 13 CO is referred as a better tracer, in our data, 12 CO work much better than this. And also you can see the actual position velocity cube came from the Apex data. This is the raw data we are using, and you can also see the spectrum in the front. So as a natural thing, we looked at the existing methods to find clumps or molecular clouds from this data. And there are many methods, also some methods that I do not listed here. So we tried every one of them, and you can see the results here. On the back, the black line is our data, and you can see different components created by these different methods. But most of them, every of them was giving bad results. So this is a summarize for every method we tried. So these are the names, and most of them were actually over-fragmenting the data. So they were coming out hundreds of molecular clouds, or they were also not seeing any clouds from this minus 40 region. And also there was a dominance feature around minus 80. So this dominance feature is also making this methods not find any cloud around it. So this actually why they are failing is that the nature of our data. So our data has some limitations. So it has a narrow field of view. What it means is we are not covering all the clouds in the data. So because these methods are actually developed for large survey data, they were not working in narrow field of view. And also our data was having a very crowded velocity axis. You will be seeing in the next slides. That was also making this methods to fail. And the last, there was a dominant feature, and it was actually dominating the founded clouds by this method. So because we couldn't reach any good enough data to put on our simulations, then we think that we can develop a method by ourselves which is tailored for our specific data. So this is a general overview of the methodology I developed. So we start with these millimeter images coming from the apex. Then we apply a peak detection to find how many clouds are there and also where are they located. Then we segmented our data, thresholded to remove the non-cloud regions from the data, and at the end we clustered them to achieve this 3D shapes of the molecular clouds. So the first step is Gaussian decomposition. Actually,
can I ask something?
Yes, sorry.
Could you explain if you go one slide back, one more back? Yeah, that one. Like, did you do this analysis with all these methods, or was this done by other people?
Sorry, Hocam.
Did you do this analysis, or was it done by other people?
I did this analysis.
So,
specific.
Could you, like, for example, explain what was the issue with k-means?
I can actually, if there is. So here is the result of k-means. We tried to optimize it by doing a hyperparameter tuning over large grid, but every time it was achieving many fragmented clouds, and it was not able to catch the dominance feature around -80.
Maybe I'll ask this in the end, but before that, maybe I have another question. Like, what is the output that you're trying to get? Do you want like a three-dimensional density sort of output in the velocity position space?
3D, only the 3D structure, the contours of the cloud. Then we calculate the NH values. Like for the composition of it, we use another data. This is just for detecting the outlines of the cloud.
I see. So it's in a sense assuming there's like a uniform density within that contour or something like that. Is that the case?
Most of the algorithms are actually trying to find a symmetric shape. That was the problem. That's why I actually tried this k-means like clustering algorithms. And actually, we ended up machine learning clustering algorithm called Misha.
Mm-hmm. I mean, k-means just gives you centers of clusters. So extracting contours from that sort of thing would also be a choice of algorithm after that. Yeah. Anyway, maybe we can talk about that in the end.
Actually, there are some algorithms doing that called Fieldworker and Watershed. They're trying to do it using the contours. So I go back to here. So I start with the first step, which is Gaussian decomposition. So in many of in some methods, they were all actually trying to fit Gaussians and achieving symmetric shapes. We influenced by them, but this is just for knowing how many clouds are there and where are they located. So we find this Gaussians and we also record their peak velocities, and we actually name this candidate clouds by M.Sc molecular clouds and their peak velocities, for example, M.Sc 80 here. And we take their peak velocities to use as cluster seeds when we're doing the cluster. And for the second step, by using this, again, Gaussians, we divide...
Sorry to interrupt. How did you pick how many Gaussians you're going to use?
We actually tried many different numbers, but many of clouds were also in the previous study of Emrah project.
Chi-square minimization.
Yeah, chi-square minimization.
Okay.
But also, chi-square minimization was given sometimes 14 or 16 clouds, but I tried to cluster them as well. So this one was giving the best results.
I mean, you can always make the result better if you add more Gaussians, right? Like you can do a perfect fit if you use enough Gaussians. So the approach should not be to make the fit as good as possible, but there should be a trade-off between the complexity you're allowing in the model versus the accuracy you want to get or something?
While we were fitting these Gaussians, I also checked the morphology and tried to consistent with the morphology I see from the data.
You mean like eyeballing and looking at how it looks or something?
Yeah.
Okay.
And for the second step, we segmented our data in the velocity space. This is both useful for when we are applying threshold, because different regions has different intensity scales. So applying the same threshold to every one of them will be a bit misleading. And also, this step is very useful when we are doing the clustering, because if we cluster low number of clouds, the computation time decreases. And also, the efficiency of the algorithm increases. That's why we segmented our data. And then we apply also thresholding. You can see some of the examples from the images on the left side. So these are not thresholded and thresholded ones. And on the right side, you can see the whole position-to-position velocity cube after applying thresholding. So after that,
what's also thresholding?
It's an adaptive thresholding method. It's by converting all the data into a histogram, it selects the threshold value from the data. And the next step is actually clustering these pixels or voxels into different clouds. So we tried many algorithms, but this comes up the best. So the intuition of this machine learning mean shift algorithm is on the left. So we start with a cluster center with a kernel window with bandwidth h. Then in every iteration, it takes the mean of the data points inside of this kernel, and then shifts the central point to a new central point. And it continues to do this until it converges to a densest region in the data. And for every point that converges to that densest region are flagged or are put in one of the clusters. So you can also see by these animations how this algorithm works in 2D and 3D.
If in this particular setting, are you clustering of the Gaussians or what?
No, we just take the Gaussians peak velocities and I just give as their seed center clusters.
Right. You mean the centers of the Gaussians? Or?
Yeah. Let's give the number of clouds beforehand from the Gaussians we fit, and also I give the seed centers, like hypothetical centers, but it's also this algorithm is also changing that center.
So, like, what's moving as you do this mean shifting would be the first locations would be the centers of the Gaussians, and then those centers you allow to shift so that you get the centers of the clusters of Gaussians or something like that. Is that right?
Yes, sir.
Okay.
So only priors we gave us the seeds, the first cluster centers where they start the mean shift, and also the number of the clouds.
How do you pick the number of clusters?
Number of the Gaussians we fit.
I mean, like, how do you pick the total number of clusters that you get from the Gaussians?
Like, we treat as every Gaussian as one cloud. So we gave...
I see. Okay, that's okay.
But only using this algorithm was not enough for our data because there was many overlaps. I can show it from here, especially in the 80 and 40 region. That's why we modified this algorithm a bit. The first modification we do is we change from hard clustering to soft clustering. what it means is it was putting every pixel or every data point, it was assigning them to only one cloud. But for these overlapping regions, you can see from the right, we need a better approach. So we changed hard assignments to probabilistic soft assignments by using a Gaussian kernel. And with using this probabilistic assignments for the overlapping regions, we divide some of the voxels into different clouds as well by using this probabilistic probabilities as the membership values for each voxel. But this was also creating an issue. It was creating an issue for over-segmentation and over-diffusion of the clouds. That's why we also introduced two pruning parameters, minimum threshold and a maximum threshold. So when we find a pixel is having a 10% probability to having in cluster A, then we check this alpha threshold. If there is some memberships below this alpha threshold, then we neglect them. And if there is one probability that exceeds this beta threshold, then we didn't divide this pixel, we just assign it to the high probability cluster. And for the hyperparameter optimization, these are the three parameters we have. We have the bandwidth coming from the mean shift for every cluster. So if we are clustering our data into 5 different clusters, then we have 5 bandwidths. And we also have alpha and beta thresholds for every segment. So we do the tuning via grid search. We score each grid's point by taking the mean silhouette of every cluster. And the silhouette coefficient is a metric used in how good a clustering is. It measures the cluster's tightness versus the separation. And after eliminating the parameters, we also use morphological regularizers for fine-tuning. And these are 2 error functions we use. So we use them to have a better physically motivated shapes. So the first one is actually shape smoothness error. It is penalizing drastic change in the morphological change over 2 segments. And the second one is penalizing the drastic change in the eccentricity of each segment.
What are I and R?
Sorry.
There's an I in the first equation and there's an R in the second equation. What are those?
These I's are actually the segments. They are one image, one velocity channel. So for a velocity channel, we look at the velocity channel near to itself. So one up, one down. This is the velocity channel in the middle, and this is one up, and this is one below.
Mean is the mean or the max?
Hocam, we are just comparing all the image.
Oh.
This is not actually subtracting, but it's making a difference in between 2 images. And these R's are the derived eigen vectors to understand the eccentricity. So we find the eccentricity of the central segment as well as all the segments. Then we again check any segment eccentricity of the segment with the segments on top of it and below it. So what we are trying to do is actually having not drastically change or more physically possible clouds.
What are these sums over? Like you have a summation over C and summation over V. Like what's C and what's V?
This is the velocity. This is the segments in every cloud, and this is different clouds. So
I can't see your hand. I'm looking at the full screen.
C is the clouds. V is
C is the cloud.
velocity segment in each cloud. For example, if we are clustering 3 clouds, we first take the summation over one cloud of different segments, and then we go to a different cloud for the next C. So we do this 3 times for every cloud. But for every cloud, we do it for the number of times.
So, like initially, you had started with these Gaussians, and then you clustered them. So each V would be the name of a Gaussian, and each C would be the name of a cluster to which these Gaussians belong. Is that right?
I'm not attacking here anymore. Only their like peak velocities are used for Cs. But the clustering is not assuming any Gaussian shape or not.
Yeah, clusters are not in Gaussian shape, but clusters, like Gaussians belong to clusters. Is that right? That's what I thought. Like each Gaussian belongs to one of the.
Yes. And each Gaussian has different segments over the velocity. So, for example, a cloud can be in 50 different segments. So it can be capturing like 10 or 20 kilometer per second region.
I see. So you discretize velocity. Is that right?
Yes.
I see. Okay. Thank you.
And after the hyperparameter tuning, we achieved our results. You can see the results. For every cloud, you can see a different color. And also to put these 3D shapes into our simulations, we also need to calculate some parameters. So these are the name of the clouds, our 15 clouds in the line of sight. And then we try to estimate their distances. For that, we use rotational curve model. And because of the nature of this model, it gives us 2 solutions, a near and a far solution. So this is the near and far distances of each cloud. And also from the cluster data coming from the apex, we calculate the integrated CO intensities. And then by using a converting factor from CO to H2, we calculated the NH values, the hydrogen column densities for every cloud. And also they are still in position velocity space. So we need to convert them into position space. That's why we also calculated their thicknesses for each of the near and far solutions.
If I don't know much about how to estimate these distances. Can you say a few words about that? You said you use like a galaxy model to estimate the distances.
Yes.
Can you explain that a little?
Here. So we are using a galactic rotational curve model because they are rotating over the center of the galaxy. By using their velocities, we can infer their distances. But because of the calculations, it gives us a near and a far distance for any cloud. So this creates a different ambiguity known as EDA, KDA.
Thank you.
And this is the final result of this 15 molecular clouds. And you can see the first step in the front. And then here are some examples of the individual shapes of the clouds. And you can also see the segments, the millimeter images that covers this cloud, and also after segmentation. And what we do after that is we take these 3D shapes and then put it in our simulations. This is done by Ahmet. We place them, actually I can go forward. We set up this simulation grid. We tried different source distances for these 3 ranges. And as I said, because we have two solutions for 15 different clouds, we have 2 to the 15 different combinations of these configurations. So we pruned some of them with pre-analysis, but we also tried many of them. And also because we didn't account for the atomic components of the hydrogen column density, we also added some normalizing factors to account for atomic hydrogen as well. And we run for all these simulations, and we created millions of simulated dust catching halos, and then we fit them to compare with the actual Chandra observation, both radially and azimutally. And here is actually a cool plot showing the same thing. So when we change the order of the clouds, the dust catching halo shape is changing. And also we look at the radial and azimuthal profile to compare it. These are the radial and azimuthal fit results. We have 3 main candidates, as you can see from the tables, 11.5, 13.6, and 4.8. So I'll go over them one by one. So the first one is 4.8. It was giving the bad, like high chi-square errors. It was giving the worst fit. But also we tried a different approach, energy-dependent analysis. So we looked at the Chandra image in 2 different energy bands, and we subtract them from each other to understand the regions where the absorption happens. Then we compare them with our cloud shapes. So as you can see from here, MC100 and MC105 is overlapping with that regions. That's why they're highly probable to be in between of the source and also to the observer, to us, to have this effect of absorption. But if the source is at 4.8 kPa, then these clouds should be farther away from the source, not in between us. That's why we ruled this distance out. And for the other one was giving both radially and azimutally the best fit results. But in the simulations, what we see is if we put our source into 13.6, then we see this second right ring. So this region is actually the ring we see from the Chandra, but in the simulations we detect another right ring, which were not in the observations. That's why we ruled this distance out as well. And as the last one, 11.5 kPa, its fits was good enough, and also there were no morphological or there was no misconclusion with any of the parameters they set. And also the NH value we found from the simulations was highly correlating from the literature. That's why we select the final solution. I'll go over by uncertainty. So we have the main uncertainty as the cloud kinematic distances coming from the rotational curve model. So it has 0.5 kPa semantic error. And also we did some assumptions during the simulations. So we calculated column density from this factor, and it has also some semantic errors coming from here. And also for the atomic components, we put some normalizing values that I showed before. And also for the scattering treatments, we assume there's only single scatterings in the simulation because we use this new dust code, but we also cross-check with a different pool ray tracing code, which is called reflex, and we didn't see much difference in between them. So our final result is 11.5 minus plus 1 kPa. And also some implications on the method I developed. So more realistic 3D morphology improves the dust interpretability, and also it helps us to constrain near-far placement of the clouds and also the source itself. And it helps us more in the azimuthal variations because now we don't have a symmetric cloud. But there's also some limitations. We have to know that this pipeline is developed for, especially for this data set, so broader validation needs to be done. And it depends on hitting thresholding and clustering choices. Still, it's a physically motivated representation. It's not a unique decomposition. And this is coming from the nature of the position velocity cube data. And its computation cost grows with the number of components as well. So as a conclusion, we tried standard finding algorithms, and they failed on narrow field of view data. That's why we tailored a pipeline to reconstruct 15 molecular clouds. And then we put them into dust scattering modeling, and we constrained the source distance as 11.5 plus minus 1 kiloparsec. And before I finish, I'll also talk a tiny about the feature work. Nature of feature work will be using other dust scattering halo sources to test this method. So we actually submitted lately a Chandra target of observation proposal submitted by Asst. And the targets we aim is this, and if we get the data, we will follow up with Apex and ALMA data to also understand the dust. But for the proposal, we did some preliminary tests. So this is the same methodology applied on a different data called from MOPA data. I again fit Gaussians and find these clusters, and I'll again put them into simulations and create these dust scattering halo shapes. And lastly, because we have many set of simulated dust scattering halo images, we think that we can use them to find new sources with training a model. But there are some problems like simulation to real domain gap. That's why we are using a software called Sista to add instrumentational effects of E Rosetta to our simulations. And then we apply self-supervised embedding and latent space clustering to find halo-like candidates in E Rosetta. And we are working with 3 undergraduates from Sabancı University, called Cem, Fatma Nur, and Nemiş. So this is the end of my talk. Well, thank you for everyone for listening, and I can answer any questions.